Hello everyone. Today I'll tell you about anti-concentration of polynomials, and this is joint work with Ohan Nguyen and Van Wu. And the main question we're going to talk about today is what is the probability that a polynomial takes a fixed value, let's say 0, over the hypercube. So this is a basic setup. I have some polynomial over the real numbers, and I'm interested in the probability that p of x equals 0, where x is uniformly random over the hypercube. Is it 0, 1, or we can choose it to be 1 minus 1 or 0, 1. 1 minus 1 is more convenient for us. Okay, so you can think of this as kind of a real version of Schwartz-Zippel lemma. So if this were our finite fields, we know the exact answer from Schwartz-Zippel-Demilo-Lipton lemma. But here we're going to look at real valued polynomials over a small discrete domain. So why is this different? So to see why it's different, let's go several years to what is known as the Littlewood-Offord problem. So Littlewood and Offord in the 1930s asked the following question. So I have a collection of numbers which are non-zero, and they studied the exact same question for the real function. So what is the maximum possible probability that the weighted sum of the xi's takes a fixed value, let's say 0. Okay? And they showed that this bound was, I think, something like at most log n over root n. Okay? And this was later improved by Erdős to 1 over root n. Okay. So as n goes to infinity, this is little of 1, unlike what happens for the finite fields. And today I want to ask a similar question for higher degree polynomials. What happens for degree 2 and degree 3 and so on. So before talking about higher degree polynomials, let's think about what the right parameterization should be. So here n was the number of non-zero coefficients. Okay? Is that a good measure when we talk about degree 2 polynomials? Well, there's one pathological example already, which is x1 times, let's say, so this is a polynomial where the number of non-zero coefficients is big, but the probability that it is 0, or let's say, is 0 is half. Right? So the measure that we are looking for should be able to distinguish these polynomials from other polynomials. Okay? So this is an important definition called the rank of a polynomial. The number of non-zero disjoint monomials of degree d in a degree d polynomial. Okay. So I have a degree d polynomial, then the rank of p is the number of disjoint monomials of degree d in the support of the coefficients of the polynomial. So for example, if p is let's say, then rank of p is n. Okay? Then you can generalize it to more things. So with this definition, let me state the theorem, which I'll state the theorem, then I'll describe some applications and motivations. Okay? The theorem is that for every p of degree d and rank of p equals r, going to be the mean of two terms. The first is I just write this as O tilde.
What's it in there? 1 over 9D?
1 over 4D. Yeah. This is r to the 1 over 4D. There are some polylog terms lurking there, so let's ignore that. But it's basically saying that as the rank goes to infinity, the probability that it takes the value 0 is going to 0, okay, at the rate of r to the 1 over d. Okay? And the second bound is going to be very good in the rank, but it has a worse dependence on the degree. So let's not worry about the exact specifications here, but let's concentrate on what the right order is. So this is saying that the probability is roughly 1 over root r up to some polylog terms. Okay? This saying is r to the 1 over 4d up to some polylog terms. Okay? So in particular, if d is O of 1, then this is less than or equal to O double tilde 1 by root r. Okay? Up to some lower order terms, it's exactly 1 over root r, just like in the linear case. So for constant degree polynomials, you're getting almost what you had for linear things. And if d is, let's say, log n over 100, then you get this is like maybe 0.001. Okay? So this is a statement of the results that you have these non-trivial bounds on the probability that a degree polynomial takes a fixed value. Okay, any questions about the statement? Yeah?
Do you mean square root log n?
Oh, okay, so I guess this 100 should be, yeah, let's say log n to the square root, then this is 2 to the minus omega square root log n. Okay. All right. So I have 5 more minutes, so let me tell you why we were looking at it and what are the applications of this.
So what's your correct answer B?
So that's a very good question. So how far off are these bounds? So right answer cannot be better than c to the d by root r. Okay? So you need to get an exponential loss on the degree, and the root r is kind of tight, just as from the linear case. Okay? So before going on, let me say a few words about previous work. So this was studied by Costello, Tao, and Wu, and then by Rasbarov and Viola before us, and they got roughly like r to the minus 1 over 2 to the d, I think. So it was non-trivial only when d was roughly log n. Okay. But we can do up to root log n or almost log n. So that's the statement of the result. It's a you can think of it as, let's say, it's a Schwarzschild de Mello-Lipton lemma for real numbers. It gives much better bounds than what you could expect for finite fields. And the applications, let me just say a couple of words. So So we were motivated to study this question from the perspective of approximating the parity function by low-degree polynomials. Okay. So this was a question posed by Raghu and Viola. They called it a challenge. So does there exist a degree log n polynomial such that the probability the polynomial computes the parity exactly is more than a half? Okay. So they asked this question. Does there exist a degree log n base 2 polynomial, say, such that it has better than random guessing advantage over computing parity? Okay. And they used that result to get, this is Raghu and Viola, no for degree less than log n. Okay. Using our approach, we can improve it to again, I'm hiding all constant factors here. Degree log n or log n. So it's still off from the challenge of log n base 2, but we are closer than before.
What do we know if we allow ourselves like 100 times log n? Is it known to do it, or what's the lowest degree polynomial that can do it?
If you allow ourselves what?
Like what's the lowest degree polynomial that
Root n.
Root n? And larger than half, you mean like 0.51 or truly anything larger?
Truly anything, any non-zero correlation.
See.
And actually, there's a deeper motivation, I think, but I can't go into it here. And so this is one application. There's another application in the same vein. Okay, let me just mention that as well. So this is so does there exist a polynomial of degree d? Okay. Oh, sorry. So take any distribution over the hypercube. Okay. So now I want to approximate the OR function with respect to this distribution by a polynomial. Okay. So I'm fixing the distribution d over n over 0 1 to the n. Does there exist a polynomial of degree d such that now I'm looking for constant correlation or constant error, 0.99 correlation. Okay. So these kinds of things appear a lot in studying AC0 computations. If you had such an upper bound, you can bootstrap it to get such polynomials for all of AC0. And using our work, we can show that the answer is no for degree d less than log n. And in a much more recent work, Harsha, Srinivasan, And Tal used our result, this anti-concentration result for polynomials, to improve it to square root log n. Okay. So these bounds are useful for studying polynomial approximations for Boolean functions, because if my polynomial is computing a Boolean function like parity or R, it places a very strong constraint on its coefficients. In particular, if the polynomial is satisfying either of these two properties, that means it should be taking a Boolean value with probability, with non-trivial probability, in which case we can use our result to say that its rank is small. And then we can build from there. So with that, let me stop. Yeah.
Like the order of quantifiers, you mean here like there is a worst case distribution? When you say the answer is no, is that there exists a distribution?
Yeah, there exists a distribution, yes. Yes. You can also think of it in the dual world, where it's asking whether or not there is a distribution of polynomials which computes the R function with error at most 0.01.
I see. And that says the reason.
Yeah.
Okay.
Yeah. So what kind of techniques do you use?
Oh, so the main technique here is the invariance principle. So in a sense, we have to keep in mind that these results are false for finite fields, so we have to use something about the real numbers. And the one thing that we know about real numbers is that there's a Gaussian distribution. So we translate the problem to the Gaussian distribution, to the Gaussian domain, and there we have very strong bounds.
Thank you, speaker.